Hello everyone, welcome to the Novedge webinar series. Today, simulating assemblies using Scan&Solve Pro. The Scan&Solve Pro structure simulation plugin for Rhino will tell you if your model is strong enough and how much it will deflect. It eliminates the need for model preprocessing, meshing, or simplifications. Furthermore, with Scan&Solve Pro, simulation can be carried out using advanced material models, including wood and laid-up composites. This webinar will show the basic steps of using Scan&Solve Pro, explain how to select and apply restraints and loads, and demonstrate simulation with those simple and advanced material models. Today's webinar presenter, Michael Freytag, is the Director of Development at Intex Solutions, and is the chief architect of the Scan&Solve system. He's also an experienced designer and craftsman who is passionate about bringing life to conceptual designs physically and virtually. And now let me tell you a little bit about Novedge. We are one of the largest online stores for design software. This is the product page where you can find Scan&Solve. But we also offer a huge assortment of software solutions that cater to virtually every designer's needs. So come browse in our catalog. You can find all the software for all your designs. And for more daily software news or promotions, you can pay a visit to the Novedge blog or follow us on all the social media out there. Coming up next week, the best features in Vectorworks 2018. And last but not least, today's webinar is free and is being recorded. So if you want to rewatch it, just head on over to Novedge's YouTube and Vimeo channel. Thanks for listening. I'm going to share Michael's screen now, so it can really show you what Scan&Solve Pro is all about.
Okay, so hopefully everybody can see my screen now?
Yes.
Okay, so today we're going to be talking about simulating assemblies using Scan&Solve Pro. And thank you for the kind introduction. So let's get started. So today's agenda, I'm going to go a little bit through motivation on why do we want to do simulation, and what advantages does it have to a traditional workflow. In particular, I'm going to talk about why Scan&Solve Pro, over the previous versions of Scan&Solve. I'm going to demo the basic operation of Scan&Solve Pro, and then I'm going to talk a little bit about wood and complex materials that we can simulate using Scan&Solve Pro, and then do a few quick demos of using these more complicated materials such as wood and composites using Scan&Solve Pro. I'll finish up with a question and answer period, but there's a few portions of the presentation which will be a little bit slow when I'm running the simulations, and during those times I welcome you to ask any questions you might have. So let's get started. So why simulation? So simulation allows us to predict the performance of products early in the design process. So here you see the typical design sequence. We start with conceptual design, we work through detailed design, build a prototype and do some testing. And typically our testing says we have a problem, so we have to go back and modify the design and then build a new prototype and do some testing. And then we find some problem and go back and do more detailed design, build a prototype and do more testing. Ideally, we want to simplify these steps or remove these steps and be able to avoid design mistakes that would typically show up in testing. So we try to identify these design mistakes early in the process. So with simulation, we can actually do this testing with a computer at the conceptual design stage and avoid design mistakes. And what happens when we do it at the conceptual design stage, this is the stage of the design process where 70 to 80% of the product cost is actually being built in. So if we can decide, or if we can use simulation early in this process like we can with Scan&Solve, we can choose designs more carefully, we can identify problems before they occur, we can avoid building a lot of the prototyping and testing processes, the prototyping and testing to destruction. We can actually do the testing directly in the computer, and we can actually do it directly in Rhino. So some of the examples I have here, this is a chair example on the bottom left from one of our users, Ian Boyd, who was actually used Scan&Solve as a diagnostic tool to identify a problem with the design after it actually had entered production. So they were experiencing a high failure rate, even though the product, the chair was designed to a standard. He was able to identify the problem and correct it in ongoing production, and reduce the failure rate to a minuscule amount. The part on the right is a part from an existing component that actually had failed in service. Ian was actually able to use Scan&Solve to identify an alternative design, a repair component that was used to replace the part that had broken. So the example, I think on the right you see actually two examples of two different designs, and I believe he ended up choosing the design on the bottom with the double ribs. So some more motivation. Why simulation? So simulation allows us to actually evaluate different geometries for performance. We can predict the stiffness, the stresses, and how the material is actually being utilized in the design. And we can use the information out of simulation to guide geometry modifications at the conceptual design stage when changes to the design itself are relatively inexpensive to do. And it also allows us to select and compare these alternative designs, as I mentioned. So across the bottom here, we have an example of a winch frame. This is a component that's used a lot in marine applications. So this particular design, on the left, we've got a factor of safety of 1.6 in this particular design. With Scan&Solve Pro, we can mix and match different components and different materials, and we can see what happens if we try different configurations of components. So in this case, we can think of this thing as a weldment. It's welded together. On the left, we've got cutouts along the side and no ribs, and a factor of safety of 1.6. The middle design, we've added ribs. We've simulated the addition of the ribs. We actually see that the factor of safety for the maximum stress is actually lower. This probably happened because the peak stress probably moved to maybe one of the components we actually added. And in the last design, we've actually removed the cutouts by, in Scan&Solve Pro, inserting components that fill in the holes. They're in red here. And we actually achieve a factor of safety of 2.5. And this is all done within minutes by adding or subtracting components from the simulation. So why Scan&Solve Pro? So like previous versions of Scan&Solve, it's FEA without meshing. So you can do simulation at the touch of a button within Rhino using solids or meshes or extrusions. With Scan&Solve Pro, we can actually now simulate with bonded assemblies. So we're not restricted to a single solid as we were with previous versions of Scan&Solve. Previously, in order to do an assembly type simulation with Scan&Solve, we would have to union all of the components of the assembly together into a single solid, which can be problematic in Rhino because the union can cause problems sometimes. With Scan&Solve Pro, we can also our components can actually be comprised of different materials. So we can mix steels with aluminums with plastics, all in the same simulation. And like I mentioned before, we can quickly try different configurations of components. And now with Scan&Solve Pro, we can also simulate with complex materials. Previously, we were limited to materials like plastics, metals, and ceramics that were isotropic. So they're materials that didn't have a preferred orientation for stiffness. But now with Scan&Solve Pro, we can actually simulate with wood and bonded composites. And again, Scan&Solve Pro is easy to use because it's integrated directly into Rhino. So let's get started and actually see how it works. I'm going to do two quick demos. I'll do a timber frame structure that shows some of the latest features of Scan&Solve Pro. And then I'll also show a winch frame example in Rhino. So you can see actually how easy it is to try different configurations of components. So we'll start with a timber frame structure. In this case, we've got a structure that's modeled, essentially it's modeled in inches. There's 54 different components here. We've got some bases that are, everything's a closed poly surface. The top is here that is timber, so it's wood. So let's go ahead and do a quick simulation on this. To run Scan&Solve Pro, we just run SNS Pro from the command line, which brings up our scenario selector. I've already got some pre-solved here, but I'm going to go ahead and create a new one. And once I've chosen this scenario, I can choose OK. And now I am actually specifying the setup for my simulation. So what we'll do is work top to bottom. We'll start by choosing a scenario, excuse me, a scenario name. We'll just call this scenario Novedge. And the next step is to actually choose the components that are participating in our simulation. And the easiest way to do this is select them by material type. So the upper structure here is made out of wood, and the bottom structure down here is these piers are made out of concrete. So I'll start by selecting the wood components. So I choose the Add button, and then I select the wood structure components. As soon as I've done that, I am presented with the material selector. So the first thing we see are the isotropic materials, like you typically see with the previous versions of Scan&Solve. But we're also presented with two new tabs. We have the wood tab and the orthotropic materials tab. So this thing is built out of wood, so we've got a number of built-in woods. I'm going to choose, it doesn't really matter, I'm just going to choose Western red cedar. Now, with wood, we have to choose a grain orientation in order for the simulation to work, because the wood acts differently in different directions depending on how the boards are cut out of the tree. So for these, I'm just going to choose rift sawn. There's a couple different versions here, but I'm just going to choose rift sawn, which is a way that the wood is cut out of the tree, so the grain is going through the thin direction. So I choose rift sawn, and that material orientation, or that grain structure, gets assigned to the components based on their mass moments of inertia, the principal moments of inertia. So the long direction corresponds to the long grain direction. In cases where the geometry is ambiguous, where the principal moments are ambiguous, I get the opportunity to actually specify the grain direction. For example, this particular component has a square cross section, so there's no preferred orientation. So now Scan&Solve is asking me to specify this grain orientation. So I will do that from a side view. So the first thing I do is select the long grain direction by selecting a point, and then the direction away from that point, and then I'm specifying the radial direction perpendicular to the original choice. And there's 4 more components that have the same sort of ambiguity, and I'll do the same thing for each of those. So our wood has now been specified, and we can apply that wood material property to the upper structure of this component, of this assembly. But we're not quite ready to actually do the simulation yet. We want to add on the piers that are supporting this whole thing at the bottom. So I choose the Add button, and then I select the piers at the bottom, and I choose the material for these. These are, I'm going to say these are made out of concrete, and I'll just choose a medium strength concrete. It comes on the isotropic material tab, and we choose Apply. So now that we've got all of our components specified, we need to specify where this thing is attached to the ground, and that's in the restraints section. So I choose Add, Restraints, and I'll select the bottom faces of these piers. So those are basically the foundations. Now for loads, there's a variety of loads we can add, but for the purposes of this, I'm just going to choose gravity. So gravity acts in the negative Z direction. And then I click Go. And Scan&Solve will go through, assemble all of these components using mathematics to decide how this thing is going to deform under the gravitational load. And in about 1 minute, we will actually see the results of the simulation. Actually, I think it's about 30 seconds. So the simulation is completed, and we can go to the View tab to actually view the results. So starting from the top, we see this is a color map of the total displacement. So red corresponds to the maximum displacement, and blue corresponds to the minimum displacement. The blue typically will be associated with the restraints, which are fixed, and the red will be the location where we've got the maximum displacement. There's a variety of solution components we can actually display. Typically, we're interested in stiffness, which we can measure by the total displacement of the structure, and we're also interested in the strength, which we can look at in terms of the von Mises stress. So if I choose the von Mises stress, we can see the locations of this assembly where we've got the high stress regions. In this case, they're right around the bottoms of the piers, and there's probably some a little bit, and you'll see it a little bit underneath the arches. In particular, I guess also along these side beams. One component that's of interest to a lot of architects is the notion of tension and compression. So we have the ability to show regions where the model is in tension and compression. So if we choose the principal tension and compression option, and if I center the scale, so if I go from negative 17.5 to 17.75 and switch the color scale to something that is just 2 colors, we can see where regions that are in compression are in blue and regions that are in tension are in red. So this is a pretty interesting way to actually look at the structure. You can see how things how they're behaving under the loads that are being applied. So here, working again from the top, we can magnify the deflection with the deflection slider, and you can get an idea of how this thing actually is deflecting. So it's greatly magnified. In this case, it's almost 7,000 times the actual deflection. But it's often interesting to actually see how the shapes deform under the loads you've got applied. We can mark locations on the model where the minimum or maximum of a particular component are occurring within the structure by clicking the min or max buttons here, which will throw in a leader that will point to the location of the minimum of the currently displayed solution quantity, and the max will show the location of the maximum solution quantity that's currently displayed. And you can hit the clear button to clear those out. Sectioning allows us to run a section through this model, and you can actually see it see what the model looks like on the inside. In this case, it's not particularly interesting because this model doesn't have a lot of bulk to it, but that is an option that we can do. Sometimes you want to isolate regions and identify, regions where maybe the stress or the deflection or the principal tension or compression is within a certain range, and you can do that by moving the legend sliders back and forth. And I think it just so there's a minimum. So it's a little odd right here, but it's throwing it off. So that allows us so you can adjust the legend limits up and down, and so you can isolate regions of the model that have particular features that you're interested in. So at the bottom, we have the ability to actually bake the shape into Rhino as a textured model or as a mesh object. So if I choose the Rhino mesh object, I can insert the deformed shape as a mesh object, which you might want to send out for 3D printing, or if you want to do a rendering of the deflected shape, you can also do a Rhino mesh object with a texture applied to it, which will show up in a render. At the bottom as well, there's a report option where we can choose to generate a report, which is it will write an HTML report, combine all of the different solution quantities into a web-ready report that you can actually look at in your browser. This will take a few seconds to do as it cycles through the components. So here's the output from that. Here's at the top we have the assembly with the geometry and materials listed. Then there's all of the components that are participating in the simulation, all of the loads and restraints that are applied, displacement summary, and von Mises stress summary. So there's reports that can be generated pretty easily. So that's the very basic, simple introduction to Scan&Solve Pro and going through the operation. I'm going to pull up the next example, which is a winch frame, which demonstrates how you can look at results from different scenarios or different component configurations and see what the effect that they have on the overall performance of the design. So in this example, I'm going to run the command again, and I've got these pre-computed because they take about 5 minutes to run each. So the very simplest example is a scenario that has no ribs. So this is just the shape without the red. So I'll just turn off these. So it's a simulation of this shape right here. And if I view the results, we can see that the maximum displacement on this particular model is 0.437 millimeters. Now, so we can generate a report and just save that in our archives for future reference. So just remember that number. And now I'm going to run it, look at it again, except in this case I'm going to look at it with the ribs turned on. Oops. So this is a simulation that includes the basic structure as well as these ribs that show up in green. And if we view the results, we can see that the actual displacement has gone down only slightly. If I use the deflection slider, you can actually see how the shape is being deformed based on the loads that were applied. And we can see that the addition of ribs actually did very little to improve the stiffness of this structure. So here you see the load that I had applied. Now I'm going to see what it looks like with these cutouts. These cutouts right here will be filled, and we can see that essentially it looks like this. In Scan&Solve Pro, all of these components basically get combined together as if they're welded or they're in contact. So let's view the results with the holes filled in, and we can see that the displacement has been cut almost in half. The overall behavior is about the same, but the deflection is much lower. And again, these take about, oh, I'm sorry, this one took 10 minutes to run, so I guess I was off by a factor of 2, 10 minutes each. And then there's a final design which combines all of the parts, which includes the ribs. The cutouts are not cut out, and we should see that the displacement on this one is marginally lower than it was before. So that's the basic operation of Scan&Solve Pro, and and just showing how easy it is to actually combine these different components and look at the simulation results very easily, very quickly, and allow you to basically consider different designs very quickly. So does anybody have any questions at this point?
Not yet, so don't be shy. This is your chance. But so far no question was raised, and I think you were very clear, and that's wonderful. What a great tool.
Okay, so continuing on. So far we've talked about using simulation to reduce prototyping costs by allowing you to do testing early in the design process and do it actually computationally instead of actually creating prototypes, physical prototypes, and doing destructive testing on them. I've shown how I've explained how we can use Scan&Solve to avoid design mistakes or identify design mistakes early in the design process and compare design alternatives. I also demoed the basic operation of Scan&Solve Pro. What I haven't talked about is how to do simulation with complex materials like wood and orthotropic composites. My timber frame structure was just a basic wood simulation using a very basic wood orientation. But I'm going to go through a demo now which shows how to specify wood that maybe has a curving orientation. So wood is interesting because it has different stiffnesses in different directions. So these directions are defined by longitudinal, tangential, and radial. The longitudinal is along the grain, and that's the stiffest direction. Then there's a tangential direction, which is tangent to the growth rings. And then there's the radial direction, which is the direction from ring to ring to ring. For any simulation with wood, we need to specify the grain orientation. In the previous demo, with the timber frame, I just selected a rift sawn, which is the orientation shown here in the bottom left, where the growth rings go across sort of the width of the board, as opposed to the flat sawn direction, which is shown in the upper right, where the rings are tangent sort of to the flat faces of the board. So when we're simulating with wood, what we're doing is specifying these orientations, and we do it with a coordinate system. And the coordinate system is labeled by color so that the red, the blue, and the green correspond to the longitudinal, tangential, and radial directions of the wood. So all the simulation with wood requires us to specify these coordinate systems. So I'm going to do a quick demo which shows how to specify the orientation on something like this, where the wood actually, the grain, because it's a laminated structure, the wood grain orientation is changing through space. So in front of you, you see I've got my laminated arch structure. I've got, I guess, 8 arches that meet in the middle. And my grain orientation follows the curve along this way. So let's go ahead and show how we do this in Scan&Solve. So I'm going to add a scenario. I've already got one computed, but I'm going to create a new one, choose OK. And I'm going to, again, work top to bottom. I add my components. The first thing I'm going to do is add these arches. And my wood, I'm going to choose, doesn't really matter, I'm going to choose Douglas fir. And in order to continue with this, I need to specify the grain orientation. I could choose rift sawn or flat sawn, or specify, which will probably work. Specify allows you to specify an orientation that's fixed in space. But the most interesting one, and the one that we're going to cover right now, is the guide method. With the guide method, we are choosing geometry to guide the coordinate system through space. So the first thing we need to do is specify the long direction of the grain. And we do this by choosing a guide curve. So, and what we've done is we've chosen actually 8 of these arches, and what Scan&Solve will do is actually iterate through these arches and allow us to specify a guide curve and surface for each one of these. So for this one, I'm going to choose this guide curve and this guide surface, this curve, and this surface, guide curve, surface, this curve, this surface for that geometry, this curve, and this surface. And what Scan&Solve will do is use the tangent of the curve to define the longitudinal direction, and the normal direction of that surface will specify the radial direction for the wood. So now I'm done specifying that, and I can click the Apply button. Now to check my work, I can click over to the Settings tab, and I can turn on the material system, the coordinate system display. And what we'll see is that the radial, or the red, and the red corresponding to the longitudinal direction is tangent to the curves we specified for each of these components. And then the blue, which is the radial component of the radial direction for the wood, is in the normal direction to the surface. So we've done this for all of our arches. Now I'll switch over to the Specify tab and then add some more wood, which is the structure here on the sides. More here. And for this, I will choose, it doesn't really matter again, I'll choose yellow birch. And then I'll choose a flat sun orientation. And hit apply. And now Scan&Solve has now recomputed the orientations, and you'll see the coordinate systems for these components, for the wood in these components, is aligned with the primary directions, or the principal directions of these pieces. And again, continuing on, we'll choose to restrain this somewhere. We'll choose the location where it's fixed to the ground. Oops. I'll do that again. Oops. So it's fixed there. And for loads, I will choose gravity again. Now, in this case, I forgot to run it up through on the timber frame example, but we can also add a load, for example, like a wind load. So I'm just gonna, I'll just do it, we'll say we have a snow load here at the top. Oops. And when I choose to apply a load, we're presented with the, I've already chosen the faces that we're applying the load to. So now I'm presented with the boundary load creator, so I can specify the type of load that I want to apply to these faces that I selected. We've got a variety of loads here. We can apply a vector force, which is a force where you enter it by component. There's also a vector force direction and magnitude where you can specify the vector direction interactively. You can specify a point and an origin, or an origin and a direction. We can also apply a scalar force, which is a pressure which computes out to a particular number of newtons of force. In this case, I'm going to choose that. So I'm going to say I've got 5,000 newtons of snow sitting on top of this. I can also choose a pressure if I know what pressure I want to apply to these faces. You can also enter an expression, which is an equation which, when evaluating x, y, and z, will have the pressure vary through space. For the marine designers, we have hydrostatic, where you can specify the water, like a hydrostatic surface, so like the water surface, and then the direction of increasing depth, and then the pressure, it will map a pressure onto the faces you've selected, which will increase with depth from that surface plane. And you can also apply torque loads. So I'm just doing the simplest here, just do a scalar force of 5,000 newtons, and that will be distributed. 5,000 newtons will be distributed among these four faces that I had selected. And that's pretty much everything I need. I'll set this to about 30,000 and hit go. With the very latest version of Scan&Solve Pro, here we've added a different set of solvers. Or actually, we've added the auto section, auto selector. So it will actually choose the fastest solver for the model your model and resolution you've chosen. Before, you would have to select the stuff manually. Now it's set to auto by default. So in this case, it's using the DSS solver because the resolution is below 100,000. And the DSS solver is sort of recommended because it's the fastest solver that we have. Does anybody have any questions while we're waiting for this to finish?
Not yet, but don't be shy.
No
Ask
questions
away.
yet.
Ask away. Ask away. This is your chance, people. Now we're all, yeah, we have our mouth open and we're gasping. So many ideas. Yeah, so many ideas. Now, so many ideas of the application of this tool.
It should be done here. There we go.
Okay.
So this is a relatively large structure, actually. It's like 5 meters by 8 meters, I think. So let's view the results. We can see what happens under a gravitational load as well, combined with a snow load. We can see that the deflection is pretty heavily concentrated along the axis or along the location where our snow load was applied. And we can actually animate that by applying the deflection slider. And you can look at all of the things. Again, principal tension and compression is usually kind of interesting. And I'll switch to something more, go -2. So you can see in this case that the underside of this arch is in tension, the top is in compression, which corresponds to, as you'd expect, as it's being bent in that direction by the load, is being compressed on the top and being pulled apart on the bottom. So that's the basics of specifying wood orientation using guide curves and surfaces. So let's go back to composites. So composites are something that we can also do on a limited basis by in the sense that we can do orthotropic composites. So composites are made by fusing several layers of material, which are known as plies, in a binding material called a matrix. Typically, the matrix might be an epoxy, and a ply might be made out of something like carbon fiber. You've probably all heard of this type of construction. Composites are nice because they're stiff and lightweight, and the mechanical properties can be customized by modifying the ply material, the number of plies, ply orientation, and the ply order. So Scan&Solve Pro supports uniaxial composites, which are composites which have properties which are typically very uniform in a cross section, but dominant in one particular direction, sort of like wood. It also supports quasi-isotropic, which are some of the most common types of composites, where the orientation of the loading within the plane of the composite, the strength of the component, the strength of the composite in the plane of the composite doesn't matter with orientation. So I'm going to show a quick example with a guide showing how the guide affects composite material properties, and also show a bicycle example. So with composites, typically composites are built from it's a layup. They call it a layup. So they start from a tooling surface and then they add layers on top of it. So we can simulate this sort of a process, or simulate the results of the mechanical properties of this layup process by using the guide curves and surfaces that I sort of demonstrated in the simple example of the arch. So I'm going to show this example, which in this case we've got you can think of this orange surface as being the tooling surface, and then the composite is built up from this surface outward, in an outward direction. But what's interesting in this example is, let's say the composite is actually laid up from that surface, but with an orientation that follows this curve. So what I'll do is choose to add this component, and we can choose from the orthotropic materials tab a variety of composites here. I'll just choose an E-glass uniaxial, or I'll do quasi-isotropic. And to use this, I need to specify, I can specify the directions explicitly by specifying X, Y, Z coordinates, or I can use the guide. So I'm going to use the guide because it's the more flexible of the two methods. So with the guide, for this particular component, it has highlighted, I want to specify the guide curve. So I'm saying that the composite follows sort of this curve. This is sort of our layup direction. So I choose that curve. And now I want the guide surface, which is this underside face, underside surface. And I choose apply. And now I can go to the settings and I can actually look to see how this material coordinate system follows the curve that I've specified. And it will do this over the entire surface. What it does is it identifies the nearest point on the curve, and from that point, it takes the tangent and says that is going to be the principal direction of my composite. The normal direction for my tooling surface gives us the build direction, which corresponds to the blue axis. So that's the basic operation of specifying the guide curves and surfaces again. But I want to show an example with where we can actually mix composites and isotropic materials like aluminum. So in this case, we've got the rear end of a bicycle, for example. I'm going to simulate this, sort of the setup for the simulation of this side of it. So run Scan&Solve Pro. I'm going to add a new simulation, and what I'm going to do is specify that I'm going to add these components. These are the composite components, which I'm going to choose to be made out of Kevlar epoxy, uniaxial. And again, I'll choose a guide for each one of these components. I'm going to choose the guide curve I've already got defined, and the guide surface. And I'll do the same thing down here. So you can think of this as being built up from a tooling surface that's in red, and the guide curve, there's a curve in there, you can barely see it moving around right in here, which is providing the principal axis for the composite layout. Now the location of I believe this is the frame stay where the wheel is mounted. I'm going to add that as an aluminum component, and you'll see that it actually fits up inside the composite frame components. And for that, I'm going to choose aluminum. We'll do a 6061. Now we'll do a 7050. Choose apply. Now for restraints, I'm going to specify where it was cut off from the rest of the bicycle. And for load, I'm going to specify a load that acts on this face, that face, where the wheel mounts, and that acts in upward and backward direction. I believe I specified 150 as well, 1500 newtons. So this is as if somebody is sitting on the bicycle and maybe slowing down, braking or something, pedaling backwards. And we choose OK. And if I go to the settings tab, we can see what the material coordinate system, we can see that it actually is wrapping around this component, each of these components. Where the green direction is basically tangent to the surface, to the guide surface, and the blue direction is pointing out normal to it. And that's the same for this. It's the case for this up here as well. Now this one takes a little bit to run, so I'm going to click done and switch over to one that I've actually already solved. And we can see the results of mixing a composite with aluminum. I'm asking a lot of my machine right now. I've got 4 Rhinos open, but it did it. So here we see the displacement plot. We see we've got 4.26 millimeters of deflection, and we can animate that deflection with a deflection slider. We can look at the von Mises stress, the danger level. I can't show danger level on composites because we don't have danger level for composites. We can look at the von Mises stress. And we can see in here that, oops, we've actually got some relatively high stress regions in here that we might be concerned about. So we might want to actually modify the geometry in these regions, maybe make this a larger fillet, or reduce or increase the radius of these fillets through here. Now, a lot of times people are interested in specifying other types of materials, but before that, I want to ask if there's any questions.
We have a very quiet audience today.
Very quiet today.
Very quiet. I know they're there. I know they're there, but there are silent partners.
Okay. So, all right, so I will continue. Let's see, what else do I have to cover here? I got my bicycle example run. Let me go back and actually just talk briefly about modifying the material properties. So if I want to, say I've got a custom material, what I can do is from the material editor, material selector, on each of these tabs, I've got the isotropic tab, the wood tab, the orthotropic tab. All of them have this custom button. So if I click the custom button, I'm presented with a material editor, which presents all of the materials for the current tab that's active. And what I can do is take any of these materials and copy them over, modify them, and then copy them back. So if I have a special ABS that has especially a weird density, say, I can make my modifications. Let's say it's softer than, it's got a lower elastic modulus and it's got a lower elastic strength. I can go ahead and make those modifications. I can also choose a different failure criterion and different tensile strength or different yield strength. So once I've done this, I can choose save, and it gets added. It'll get added to the list. So ABS2 just got added down here. I click OK. And down here at the bottom, you see that this is now an option for one of my materials. The same thing applies with wood. The challenge with wood is coming up with all the mechanical properties, because it's difficult to find material properties for wood that covers all of the categories that are required for Scan&Solve to operate. But again, if you have them, they can be entered. They can be entered directly, or you can, like I said, take an existing material, copy it over, and modify it. So if you have, say, a white oak that's similar to red oak, say you know that it's stiffer, you can take a red oak and modify it in a way that makes sense to you. And the same thing with the orthotropic composites. The literature on these is probably more extensive. But again, it's often a challenge to find the mechanical properties, but they're out there. So that pretty much sums up everything I had to talk about. But I do recommend that you download Scan&Solve and try it out for yourself. The website is intactsolutions.com. The link is actually shown here. The documentation. Let's see if I can go to this page. Was recently updated, so we can, it should all be up to date. So here's the documentation on Scan&Solve Pro, how to get started, different materials, doing restraints, loads, results. And then there's additional learning materials that can be used to if you have particular examples, it works through some examples to show the effects of different simulation quantities, or different simulation situations. We also have a YouTube channel where you can see videos of new features as they get added, or a lot of times we have webinars that I think get posted there. You can visit our forum where you can ask questions and get answers. And if you have anything that you have any questions on, go ahead and email us at support@dentechsolutions.com. So if you want to purchase Scan&Solve, you can go to Novedge. Here's a link for Novedge. I think Barbara showed that earlier, but this is Scan&Solve Pro on Novedge.
Yes, and I have a question. Actually, it's relevant. Does Scan&Solve work as a standalone application, or do you also need a seat of Rhino? I know the answers, but let's clear it up once and for all.
It works within Rhino, so it's a plugin for Rhino.
So you do need Rhino.
Is required, yes.
You can just, it's not all included, it's not a bundle. The Rhino is not included when you purchase Scan&Solve. You also have to purchase Rhino if you don't have it or have it already installed. Which, yeah, great. So that was the only questions we had. And usually, it looks to me like you really thought of everything. So usually we get a question, oh, can you add this, and what about this? And I guess really you guys thought of everything. And
well, if anybody has any questions that come up later, please feel free to email us.
Great, yes. Thank you for being so available. I'm going to take the screen back so I can wrap up the presentation, and hopefully you can see my screen now. Yes, I want to thank everybody for attending today's webinar, and I want to remind everyone to visit our page at novedge.com, where you can find both Scan&Solve Pro and Rhino. And next webinar will be about the best features in Vectorworks 2018. And to watch today's webinar or previous ones, check out our Novedge YouTube and Vimeo channels. Our webinar playlist as webinars for every software taste. Thanks again for joining us today, Michael, and thanks everybody for spending an hour with us. Have a wonderful day. Bye-bye.
Bye. Thank you.